Hi, I'm Matthew Solomon. I'm the distance master in this project. My role as a distance master is that I understand all the distances that the Super Soaker may travel. I also understand the distance and number of pumps relation when it comes to like graphs and stuff like that. As the mathematical master, I'm tasked to solve all the math problems that we encounter in our project. This may include, some simple math like having an equation and plugging in numbers into that equation, and it may even be a little more difficult stuff like that than like finding like the slope of a trend line on a graph or something like that. Alright, now let's see what Evan has up his sleeve.
Welcome guys, I'm Evan Creek, and in this project I'm the Super Soaker engineer and the graphical analyzer. So as a Super Soaker engineer, I understand how a Super Soaker works and how the pressure and number of pumps relates to the amount of distance the water travels. Also, as a Super Soaker engineer, I design and build new prototypes to help better suit for new Super Soaker guns. As a graphical analyzer, I understand and focus on how the graphs are related to the data. Also, I make these graphs and understand how we can use them in this data to help answer and solve problems.
Welcome, Evan. Let me get some background information on this so-called Super Soaker.
I got you. While some might not believe, Lonnie Johnson, the inventor of the Super Soaker, invented the squirt gun by accident. Johnson has over 120 patents on various different projects. These include lithium film batteries, electrochemical conversion systems, heat pumps, generators, and various items to enhance battery production. Also, Johnson has various patent concepts like hair dryer apparatus, wet diaper detector, toy rocket launcher, and Nerf blasters. Johnson also invented a common invention that is used today. While at the U.S. Air Force Space Mission Lab, he patented a device that reduces a binary code to scale. Then using a magnifying lens and sensors to retrieve the information, this is just the basic technology that is used in CDs and DVDs today. So back to the Super Soaker, Johnson was at home working on an improvement for his heat pump in his house that recently broke when his creation sprang a leak. The burst of water shot across the room, and the first thing he thought was that would be a great Super Soaker.
Wonderful. Now that we got some background information, let's cut to an experiment. Thank you, Matthew. Now it's time for our experiment. Alright, so this is test experiment number 1. We're going to be seeing the relation between the distance traveled and the number of pumps that is used on the Super Soaker. Alright, so I'm going to apply 23 pumps onto the Super Soaker, and we're going to just see how far it goes, alright?
This is so crazy. With 23 pumps from our Super Soaker, the water flew 252 inches.
Alright, now that we did test experiment number 1, it's time to analyze our data. Thanks, Matthew. Now it's time to analyze our data.
Welcome, Matthew. I heard that you are good with knowledge about these Super Soakers and how distance and the number of pumps are related. Could you tell me what affects the distance the Super Soaker will shoot the water?
Yeah. So from our findings, I figured out that distance is determined by the amount of pumps that you put into the Super Soaker, right?
Okay.
So the more pumps you add means the more pressure you're building up onto the Super Soaker, so the farther the gun's gonna shoot.
Okay. Could someone predict the distance of the Super Soaker?
Yeah, you could predict the distance. We conducted an experiment where we shot the Super Soaker with a certain amount of pumps, and we put it onto a graph, right? And from this graph, we came up with the equation y equals 84.491 natural log of x minus 87.6.
Oh, okay. That's cool. Is the amount of water expelled per shot from the Super Soaker dependent upon the number of pumps, or is there anything else that could change the distance?
I mean, yes and no. The first 40 pumps, the distance is dependent upon the number of pumps.
Okay.
But then, as you increase it, past 40, it starts to flatten out. So it barely will start to increase.
Okay.
Thank you, Matthew. Next, we'll be talking about our graphs. The graph in front of you see is our distance versus number of pumps graphs. Along the x-axis, we have the number of pumps, and along the y-axis, we have the distance in inches. As you can see, our graph isn't really linear. It's more logarithmic. The trend line that we were given shows us an equation of y equals 84.491 ln x minus 87.96. We would use this to be able to calculate or predict how far the number of pumps, the x, would get us in distance, y. The next graph we have is another distance versus pumps graph. Along the x-axis we have our number of pumps, and along the y-axis we have our distance in inches. This graph is much different from our one before because it's linear instead of logarithmic. Our equation we got from this graph was y equals 15x minus 2. We got this by plugging this into Excel and giving us a trend line. The reason this distance is linear is because of the data that we collected from our problem. The number of pumps was 5, 12, and 25. The distance we got for this was for 5 pumps, 73 inches, for 12 pumps, 178 inches, and for 25 pumps, we got 373 inches. When we plugged this into Math Excel and then graphed it, we got a linear line shown below.
We'll talk about our analysis. From viewing the results that our group had collected during examination of these statistics we were handed, we can conclude that a relationship between the number of pumps and the distance the water travels creates a positive logarithmic graph. Some of the strengths of this were there weren't any outliers on our graph, and the equation we came up with gives us an extremely accurate solution. Some of the weaknesses is it would be really difficult to keep a steady angle when measuring this data, and there were a ton of constraints, and if one of the constraints were manipulated, then our entire data would be invalid. One potential improvement that could make when finding our data would be having a way to keep the Super Soaker at a constant angle at all times. Maybe propping this up on a tight stand that doesn't allow movement would be really helpful for finding some precise information. Okay, this is the new Super Soaker design we have right now, and I'm thinking that this is going to get us the most amount of product with like the most amount of cells, and it will give us the best distance.
I don't think it will. Look at there's not enough, you're not going to get enough pressure from that pump. We need a longer tube for the pump so we can get more pressure building inside the gun.
I think you're just wrong.
I think you're just wrong.
Dude,
I'm sick and tired.
Let's take it outside.
Let's take it to the hall.
Take it to the hall.